2b goes to question 11. For the reaction 2a plus 2b goes to c, rate equation is, and you're given a nice little rate equation, which of the following could be a possible mechanism for this reaction? Okay, so looking at this rate equation here, what you see is that you've got 1a that's involved in the rate limiting step, and we have 2b's involved in the rate limiting step. That's really what this is saying. So what we're looking for is a slow step that involves this, because the fast will not be rate limiting. Okay, so for A, I've only got 1A and 1B. Nope. For B, I've got 1A and 2B's. I like this one. Just to check, this one's got 2A's and 1B, so that's out. And this one has 2A's, oh sorry, that's the fast. This has just 1B. So that would have been a rate equation saying that. Okay, so definitely B. Right, which line in the table has the correct number and type of bonds in the structure shown? Right, you could make your life very, very easy here by recognising that the pi bonds, there are actually only 2, okay, and it is actually really only one of these ones in here. The other one in there is a sigma. So there's your 2. And then just to do your count, let's just change this colour here. 1, 2, that third one in there, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. But you could have got that answer just from the 2. Okay. 5-methyl hept 3-ene-2-one is an aroma molecule found in some types of tea. Which of the following shows a structural formula for the trans isomer of this one here? Okay, so I'm just going to draw it out and then deal with it later. It's kind of how I felt it's the easiest way to deal with this. So I'm going to put, for a start, my longest chain is a hept, so a 7. So that's 1, 2, 3, 4, 5, 6, 7. Okay. I have hept 3-ene. 1, 2, 3, I'm going to put my double bond there. And then I'm going to look for 5-methyl. I've already decided this is number 1. So 1, 2, 3, 4, 5. I'm going to put a methyl group down here. And then I'm going to put 2-one. So on number 2, I need a double bond O. Now obviously this could be spun round. Let me just clean that up a little bit. Oh, that was not supposed to happen. 1, 2, 3, 4, 5, 6, 7. And there was my double bond. Okay, so this could be done in any orientation whatsoever. And in fact, I do have to kind of flip it around because it's this one here. Okay. The following does not, in bold, so therefore important, exhibit hydrogen bonding between its molecules. Okay, so hydrogen bonding, I'm looking for a hydrogen bonded to an N, an O, or an F from higher. Okay, so you can sit and draw them out. Ethanol, right, well that's definitely going to have hydrogen bonding. Ethylamine, I've got nitrogens with hydrogens on here, so that's got hydrogen bonding. Ethanoic acid, we know has hydrogen bonding. Ethoxyethane, however, is an ether. Okay, I've got 2 carbons, an oxygen in the middle, another 2 carbons. This oxygen here is not connecting to hydrogens, and the carbons are no good at producing hydrogen bonding, so that's why that one's right. In the homologous series of amines, an increase in chain length is accompanied by, okay, so we are looking at volatility and solubility. So solubility is to do with how much they like being near the partial charges, which I am expecting to see in water, okay? So I need something that's polar. The more polar something is, the more soluble it is. They're saying increasing chain length. So an amine is going to have nitrogen at the end, which is going to be super good at sticking to this. It's going to like nice wee hydrogen bonding going on inside with the water. And then we've got a chain that's going to come off this side. And the longer that chain is, the more this molecule doesn't like water. This is non-polar. Okay, so the longer that squiggle gets, this just can't outweigh it. So solubility in water as I increase chain length is going to decrease. Okay. Volatility, so how easy it is to evaporate. Well, basically, and do other things. This one, the bigger it gets, the less easy it's going to be to make it volatile. Okay, so B for that one.